Okay, I think we are good. I- Right. Thank you for your patience. We had a little bit of a kerfuffle getting into this room on time, so that happens. But we're here. Good journal. Thank you all for all coming out. I'm Jason, speaker coordinator for the San Francisco Amateur Astronomers. And just to let you know, we have a few very exciting events coming up. One being our next one is the City Star Party, December 13th. Definitely want to come to that. Um, Also, if you are a member, one of the little perks we have is an end of year party that happens every year. That's coming up later in December. You can only see that if you log into the website, so that you're just browsing, not logged in, you're not going to see it. But it's going to be a fun party. We've got the best people on the job here. I see Jean in the audience. She's been working a lot. Vicky also has been doing a tremendous amount of work getting ready for this party. You want to be there. I'm not going to spend much more time talking than that. There are a lot of benefits being in the San Francisco Amateur Astronomers. I hope you're all enjoying it. This lecture is being one of the perks. We are very pleased tonight to welcome Dr. Robert Douglas, who is a regular among some of the star parties a little bit further north at Sonoma. He's also a member of not only the San Francisco Amateur Astronomers, also East Bay, Tucson, going a little further from home, and Planetary Society, and is a longtime professor at San Francisco State. Um, and I've read his book personally. It is a phenomenal book, extremely entertaining, and he's going to take us through some of the highlights of that book. So I do hope you enjoy it. We're in for a treat. Thank you.
Well, let me thank SFAA for inviting me, in particular Jason. I think I met him first at Lake Sonoma when we both had telescopes up there, and that's how we met. I'm going to be talking about certain sections from this book. The title is there. Basically, that's the cover. That's, of course, Eta Carina, one of the most magnificent objects in the night sky. You have to go south to see it. Basically, I wrote this book in 2022. It's not that. And I aimed the book for amateur astronomers or in general anyone interested in astronomy. And it sort of has two features to it. One is I collected a lot of articles with about astronomical facts. A lot of them were rather shocking. You say, "Oh my God, is that really true?" And so the sort of wow topics. Well, I threw a bunch of them in the book here. But I also describe or explain various astronomical phenomena. And in the back of the book, there's an appendix where there's a fair amount of mathematics. If you're not so inclined, you can just skip it. Most of the mathematics is back there where I basically verify everything that I say of mathematical nature in the book. And there are 59 topics. This isn't a book about one subject. There are 59 topics, and some of them are longer than others. But the idea is there'll probably be several dozen that you're interested in, more than others. You can pick and choose what you want. So, and as I say, there are 59 topics, but let me just give you a few of them. I've listed 17 here. The tides, the auroras, the fate of the sun, total solar eclipses, the Saros cycle, the Saros series. Why is the moon tidally locked to and receding from the Earth? What about other moons? Could a moon have a moon? How is the diameter of a star determined? There's something called the Yarkovsky effect, the illusion of superluminal speed, the explanation of the grain flash, together with the surprising fact. In fact, that's why I included this. It's that one of the shocking facts even advanced amateur astronomers didn't even know. And there's the Hertzsprung-Russell diagram. Why does one see more meteors after midnight than before? And then orbital resonance. How could Aristarchus of Samos, who lived about 300 BCE? By the way, I'll be using CE for current year instead of AD, and BCE for before the current year, which is what scientists use instead of the other. He managed 300 BCE, he managed to figure out the sizes of the sun and the moon and their distances from the earth using geometry and a few measurements in terms of the distance from the earth to the moon. That's pretty good. And Steven Weinberg, who was a Nobel laureate in physics, said that he was really maybe the first scientist who really used what you might call modern scientific methods. Exoplanets and asteroid comet collisions. Those are just 17 of the topics, but there are a lot of others. Oh, here is a site where you can go to. As Simha is a well-known amateur astronomer, and he set the site up. You could go there, and there's a topic 60 there. I said the book has 59. Well, I thought I might include some others. And after you write a book, you say, gee, I just found out a fantastic topic I didn't include. Well, this one, topic 60, is a very simple explanation or calculation. If you ask the question, suppose that a exoplanet is circling its star and the orbit's circular, that makes the math a lot easier. What's the probability from the Earth you can see that planet crossing the face of that star? There's actually a simple mathematical way to come up with a formula for that. That's topic 60, but you have to go to this website to see it. There's also a review of the book by a very well-known amateur astronomer in Oregon, Mel Bartels. There's a link to the Amazon site where you can buy the book, and then there's other information. Okay, I'm hoping I can get through all these topics. We'll see. The first one is, Pluto has 5 moons, and the biggest one is Charon. And it's about half the size of Pluto itself. Pluto is about 1,500 miles in diameter, and its moon, Charon, is about 750, and these are images. And question, if you were on Charon, if you were on Pluto, how big would Charon appear in the sky? Well, first of all, these two objects are tidally locked to each other. So each always has its same face facing each other. Our moon is tidally locked to the Earth, but the Earth is certainly not tidally locked to our moon. So that means if you're, say, on this side of Pluto, you would never see Charon. But if you got in your little Pluto car and drove around the other side, all of a sudden this huge object would be there. And by the way, how huge would it appear? Well, the answer is about 7 times the diameter of our moon. So it would be pretty big. And it would, if you stopped on wherever you were on the other side of Pluto, it would constantly be in the same part of the sky. And of course, if you were on Charon looking at Pluto, you would always just see the same face. Okay. I just might add that since the mass of Charon is half the size of the mass of Pluto, that these really are almost twin planets in the sense that they're circling the same center of gravity. And of course, our moon and the Earth, there's a barycenter, there's a center of gravity, but that center of gravity is well inside the Earth. So we just say the moon circles the Earth. But here, the barycenter, the point at which these two objects are rotating, is not in either object. It's in between them. And they're only about 12,000 miles apart. That's pretty close. So, boy, that's itchy twitchy. Oops, we're going the wrong direction. Okay, let's move on. Okay, there's this object, Miranda. It's the 5th It's one of the 5 major moons of Uranus. It's the smallest, about 300 miles in diameter, and it's the closest of the 5 moons. And it's in the running for the most bizarre moon in the solar system. Because, as I wrote here, it's a hodgepodge of dissimilar terrains. It looks like the regions have been sewn together like Frankenstein. And if you were actually on the surface of Miranda and you looked up at Uranus, well, this is pretty close. Now, first of all, Uranus would be a cyan, a bluish green color, because of the methane absorbing the reddish light. But this Uranus would be about 22.5 degrees in the sky, about 45 times the angular diameter of our moon seen from Earth. So this would be huge. And as I said, Uranus's color is caused by methane absorbing red light. This image was taken by Voyager 2 when it went by Miranda in 1986. It could only image the southern hemisphere, so we don't know what the bizarre side of the opposite side of that would look like. When the NASA scientists had these images coming in as the Voyager craft was going by, they couldn't believe what they were seeing. Nobody imagined anything like this. Ooh, that's a tricky thing. There's a famous physicist named Isadora Rabi who, there was a subatomic particle, the muon. When it was discovered, no physicist had any idea, nobody had predicted this, and his famous statement was, well, who ordered that? And, well, you could say the same, the NASA scientists could say, well, who ordered this? By the way, just if you want a little way of remembering the moons, the 5 major moons of Uranus, just remember M-A-U-T-O, Mautu, Miranda, Ariel, Umbriel, Titania, and Oberon. Those are the moons, 5 major moons of Uranus in the order from closest to farthest away. Let me point out a few things here. This has the highest cliff in the solar, highest known cliff in the solar system. We're going to be looking at some images of it in a moment. But I want to just point out a few things. There's this. Can everybody see that red line?
Yes.
I have a green laser, but I don't like to use them. They're too powerful. There's the chevron. This is looks like this Circus Maximus in Rome, and there's some straight lines here which you don't usually see on natural objects. Okay. Oh, the cliff in this image is right down there. So let's take a closer look. This is a closer look. And here's what I call the Circus Maximus. There's the chevron. There's the cliff right there. It's called Verona Rupes. And, okay. Here's an even closer image right there. Circle red. There was this is an imaginary image of the top of that. And you might notice, I don't know, it's pretty small, but there's some astronauts here. There's one of them right there jumping off the edge. Okay, well, what's this on? By the way, this image here is by a fellow named Eric Lundquist, who made a short film called Wanderers, and was written and narrated by Carl Sagan. Now, what about those idiots up there jumping off? What are they doing? They're having fun, basically. It's bungee jumping on the big top. Well, let's talk about how high that cliff is. I said it's the highest cliff, known cliff in the solar system. Well, what about the Earth? Mount Thor on Baffin Island in Canada. It's the highest cliff on the Earth. The mountain is about 5,500 feet high, about a mile. And the cliff actually is about 4,100 feet, and it actually overhangs at an angle of 105 degrees, so it's steeper than vertical. Well, I made a schematic here to indicate the relative size of Verona Lupus to our highest cliff. Here's Verona Lupus, 63,000 feet. And here we have Mount 4,100. So they're jumping off that. Well, hey, this is a small object, 300 miles in diameter. It's not as massive as our moon or by any means. Okay. But it's 12 miles high. Now, if you jumped off the top, it actually take you 12 minutes to hit the bottom. So, all right. And at the speed, what speed would you be hitting? 125 miles an hour. Well, maybe you want to jump from a little lower and maybe have an air mattress at the bottom. But, and by the way, these calculations, like why would it take 12 minutes? Why 125 miles per hour? Go see the appendix for the calculations. Okay, see, as I said, there are 59 topics. And if you're not interested in one, hey, here's something completely different. That's certainly different from random. Okay, this is the emu. It's endemic to Australia. It's the second largest living bird after its relative, the ostrich. So why do I bring this up? Well, this is the night sky from Tasmania. And the natives, the Aborigines in Australia, they not only looked at stars and formed patterns like all people on the earth did, creating constellations, they also took darker regions, especially in the Milky Way, and made animals on it. And here's the great emu. There's the button. There. This is the great emu here. Sort of make it out. And by the way, this is a T-shirt. There's the great emu. This is a T-shirt given out in 2007 of the deepest South Texas star supply. Now you might say, this is a sort of a fun name. Basically, it was a star party organized by people in Texas and Coonabarabran, well, people in Australia, and it took place in Coonabarabran, Australia. So they made that name. At any rate, by the way, this is the whole sack up here. That's the head of the great emu, and that's the body going down. Okay, I'm going to run through a number of objects in the southern hemisphere, trying to get you. This is the coal stack right here. Now it looks like there's a lot of stars. If you're in the southern hemisphere and even looking with a small telescope, it's going to be pitch black. And this is in Crux. There are 88 constellations. Crux is the smallest, but there are only 20 first magnitude stars. It's got two of them. And one of them is Beta Crucis, this one right here. And if you have even a small, very small telescope, and you looked at Beta Crucis, you would notice a very bright red star near only 2.4 minutes to the west. It's actually a carbon star. Those are the reddest stars in the sky. Its name is DY Crucis or Ruby Crucis, and there's a crude scale for determining color. It's the B minus B scale. B is for a blue filter. It blocks blue light. V is for visual, allowing green and yellow, which is the main part of the visual spectrum. It lets that light through. And if you take photometers and measure through those two filters and subtract one value from the other, generally white stars are going to be around 0. Blue stars are going to be a negative B minus V value. Red are going to be a positive. And about the reddest you can get is about 5.8, and that's what that means. Whoops, didn't mean to do so. Okay, this is just another sort of interesting object, not one of the most famous ones, actually, it's more obscure. But the Australians have lovely names for everything in Australia and in the sky. It's called the dark doodah. And it's a vertical streak in the constellation Musca, And there is a globular cluster right here near it, NGC 4372 at the southern end. This is another interesting object. Actually, you can see this from latitude in California, but of course it's much higher in Australia. This is a globular cluster, and the globular cluster, I think most people know what they are. It's called the Chandelier Globular Cluster, NGC 6723. And here we have what's called, another colorful name, the field of nothing. And that's just basically, there's a lot of dust there blocking out all the starlight behind it. It's not a giant hole for the stars, they're behind it. And these are reflection nebulae here. Reflection nebulae are hydrogen gas, which is not emitting light itself, but there's stars embedded in the nebulae, and the starlight is being reflected in the gas. Okay, this is my favorite galaxy in the southern hemisphere. It's called the Large Spiral, and I think it's pretty obvious why it's called the Large Spiral. There's that. And there are a couple of large spirals. The two best ones in the northern hemisphere are NGC 7479 in Pegasus and NGC 1300 in Eridanus. But if you look through an amateur telescope at those, you might say, let me see. Where's the bar? Maybe I can see. Well, hey, nobody's going to miss this. It's in your face. That's why as an Australian friend of mine, he called it the largest orb. This is a spiral galaxy twice the size of the Milky Way galaxy. Ours is about 100,000 light years in diameter. This is about 200,000. And so it is really a magnificent thing to see in a small telescope. Oops, went too far. Okay. All right, this is a very unique object. It's the star Eta Carina. It's about 7,600 light years away in the constellation Carina. Now, obviously, that's why it's called Eta Carina. But it's in a giant nebula, which is one of the greatest nebulas to see from the planet Earth, NGC 3372. Now, this basically, in 1840, there was an explosion, and these balls of gas shot out to two sides. And then in 1847, there's a minor explosion in this direction. Now you'd think, okay, I'm going to have to look through a professional telescope to see this. Not true. If you have a little 8-inch telescope, you can see them. This is called the homunculus, the little man in Latin. And you can see easily these two balls. And with a slightly smaller telescope, you can see striations in these two gas balls. The actual sign, this is orange, very weird color in the sky. And it's actually 16 arc minutes, 16 arc seconds by 12 arc seconds. And if you're trying to split double stars, you know it's 1.5 arc seconds, 2 arc seconds. That's pretty big. Easily seen, and it's really one of the most incredible things in the sky. It is a super candidate. It's a supernova candidate. Whoops, just boy, that's really twitchy. It's actually two stars they've discovered. There's Eta Carina A, that's its orbit. That's its orbit, and Eta Carina B, they discovered that. And they come fairly close to each other, so they're two of them. And Eta Carina A is, as I said, so it's a candidate for being a massive supernova. And to give you an idea of the scale here, this is 16 astronomical units right here. Oh, did that on its own. Okay, I said that the Eta Carina is inside the Eta Carina Nebula. And this is the great Eta Carina Nebula here. And NGC 3372. And the star Eta Carina is basically right there. And what's this here? This is this little thing here. This is called the keyhole, and it's just slightly to the right of Beta Green itself. By the way, there's something called the keyhole in Orion. This has nothing, obviously, to do with that. So this fills up a large part of the sky in the telescope. This is enormous. Okay, here's just a shot of the sky from Chile. Here's the Milky Way. By the way, from the southern hemisphere, you get to see all of the Milky Way throughout a year, but from the northern hemisphere, we miss out on some of the best parts, namely Korea. The Large Magellanic Cloud and the Small Magellanic Cloud look like parts of the Milky Way detached from the Milky Way. But as you and I know, that's not the case. The Milky Way galaxy is about 100,000 light years across. The Large Magellanic Cloud it's about 160,000 light years from us. The small one is about 204,000, so they're outside. They're dwarf. They're satellite galaxies of the Milky Way. And these two objects, in reality, are separated about 80,000 light years. And of course, whoops. Okay, this is the Large Magellanic Cloud. And there are people that specialize, I know, some people in Australia, they specialize in just objects inside that. And there are a lot of globular clusters, emission nebulae, all kinds of things. And this is the Large Magellanic Cloud. Now, what is that creature? One of the top 5 objects you can see from the planet Earth. It's truly amazing. The Tarantula Nebula. We're going to look at some more images of that. Okay, here's a close-up of the tarantula. The Orion Nebula is 25 light years away. The Tarantula Nebula is 1,000 light years. What if the Tarantula Nebula were as close as the Orion Nebula and you're sitting on the Earth looking at it? Well, everybody here knows M42, my nebula. It would cover the sky with a diameter of about 36 degrees, filling the entire constellation of Orion. And the angular distance between Rigel and Betelgeuse is about 17 degrees. So this would cover the entire constellation. And just imagine if you were in the Small Magellanic Cloud looking at the Tarantula Nebula, what that would look like. It would be in all the 4 worlds of all whatever creatures live on the planet that we're looking at. And I think the only people that wouldn't appreciate this are those suffering from arachnophobia. Yeah, did we see something here? No, maybe it must be done. Okay. This is a close-up view of what's called R136. It's the star-forming region in the Tarantula as seen in the Hubble telescope. There it is right there. And let's just look back a little. What happened? I got all that stuff there. Okay, good. Let's go back. That region I think that region is right in there. But we'll move on. Okay, this is the Small Magellanic Cloud, the one that's 204,000 light years away. And there are 2 globular clusters nearby. That's 47 Tucana, the second largest globular cluster you can see from Earth, Megacentauri being number 1. And it's that's another globule right there. They're only about 17,000 light years from where we are. They're not associated with this cloud, which is 204,000 light years away. Here's a closer-up view of 47 Tucana. As you can see with the naked eye, 4th magnitude, and it has a very dense center. And here is a megacentauri with maybe its 10 million stars in it, and it has an angular diameter of the moon. And it is a truly awesome thing to look at. And some astronomers now believe it's not. By the way, it's the largest one known, and it's one of the closest. But some astronomers now think this is not a globular cluster, it's the core of a dwarf galaxy that's lost a lot of its stars. And they think there's a black hole in the center. And one of the reasons why they think it's not a globular cluster is because globular clusters, all the stars tend to be the same age, and there are a lot of stars of different ages in this, so they're suspicious it's not really a globular. The green flash. First of all, how many have heard of the green flash? How many have heard of it? Wonderful. How many have seen the green flash? Very good. Okay. All right, let's talk about it. And this surprise fact. Okay, this effect can be seen for a few seconds at sunrise or sunset. Let's talk about sunset. Just when the sun's going down, just at the top, as the top of the sun reaches the horizon, if you're lucky, the last rays will glow green. And it usually occurs when warmer water is close to the ground and cold air is above, and that's frequently the case over water. And so it's usually a good idea to try and have a body of water. Okay, I want to talk a little bit about how this happens. What's the geometry of the green flash? The situation is that the sun's image appears to the observer to be about a half a degree higher than its actual position. Suppose you're right here, you're on the Earth, this is the atmosphere, you're on the Earth, this is your horizon, and the sun is just below the horizon, but because of the refraction, the light from here comes up here, and is refracted by the atmosphere down there. You look up here, and you see the sun. And it just so happens that when the sun is right here, half a degree, its image is up here, and you think it's still up there, but it isn't. If we didn't have an atmosphere, you wouldn't see it. Now, I've simplified things. I've got the light coming from the sun, and when it hits the atmosphere, it goes in a straight line down to the observer. That's technically not the case. Really, it's a simplification. What really happens is the light is coming up here, but the atmosphere, the density of the atmosphere changes. It gets denser as you go down. That's causing the refraction, the light to be fracted into a curve. And so you would be here, this light would come from the sun, curve down, you look up here, and oh, there it is up there. If the atmosphere were just solid glass, it would be refracted down in a straight line. Oops. Okay. Now, of course, we're talking about color. And so we have to introduce the different wavelengths of light. Light is made up of all the colors of the rainbow, all the different colors. So what happens? Here you are. Here's the light ray coming from the sun. It hits the Earth's atmosphere, and I'm simplifying. It's going to come down in a straight line in these diagrams. But different wavelengths of light have been refracted differently. Green light is refracted more than red, and all the colors in between are refracted at angles in between. So what happens? Here comes the white light, it's refracted down, and if you look back, the red, you can see red below green. Red below green. Okay. So the result is the overlapping red, orange, I say yellow, green, and blue image of the sun. They're overlapping, and where these images overlap, we get white light. Now, there'll be a slight sliver of red at the bottom of the overlap, and a slight sliver of, okay, blue. I'll say in a moment why I didn't put blue here. Hang on. But just above the, there'll be a sliver of green just above. The blue ray, the reason why the blue is left out is The blue light coming from the sun is going to be due to Rayleigh scattering, scattered by the nitrogen atoms in the atmosphere, and that's why we have a blue sky. So that blue light gets scattered all over, and you're not getting much blue light coming to your eyes. So, okay. And by the way, one might say, I keep saying you get what? Let's move to the next. Yeah, let's. Here we have the sun. It's yellow there. There's the green at the top and the blue at the bottom. Okay, and the reason why, well, it's yellow here. It should be white. I'll say why it's yellow in a moment. But when all of the colors overlap, you get white. So you might say, how come it's yellow? Well, if you're in the International Space Station on the moon, it's white. Why are you getting yellow? Well, I just told you why. The blue rays coming from the sun get scattered in the atmosphere. You're not seeing blue. So all of the wavelengths of light coming from the sun is missing the blue and shifts the color of the sun slightly toward the red end of the spectrum, so you get yellow. Okay. Here, by the way, is an image of the sun. This is the Golden Gate Bridge. And you can see a little green up there and a little red right there. Okay. And everything else that's overlapping, and you get the yellow in this case. Okay, let's talk about the best opportunity to see the green flash. It's, as I said, it's at sunset from sea level. You want a clear view of the western horizon, maybe a body of water. And the transparency of the air is important so that there not be too much water vapor. I mean, red light is absorbed more by water vapor than green, but if it's humid enough, the green will be absorbed and you're not going to see the green flash. I might add that if you're a photographer and you're looking at the sun setting, your eyes are going to be affected by the fact you're staring at a orange-red sun for a few seconds. It's enough to make most flashes to the eye appear green at a stage when they photograph is yellow. So people don't trip the proverbial shutter too soon, and they don't get an image of the green flash. You have to be aware of that. Just an intriguing thought. Suppose that you were at the North or South Pole and the sun were at either equinox, in other words, over the equator. Then the sun would be circling the entire horizon all day, and so maybe you could get some green flashes, especially if there were some objects, if it were regular terrain. Well, North Pole, South Pole. You want to be at the South Pole, the North Pole just flat, but it'd be pretty cold, and nobody's going to do that. I might add that I've only seen the green flash twice, and it was with Fran. We were on a Home to America ship, and 2 nights in a row we saw the green flash. And I've tried to see it many times, and I finally saw it. There it was, but many, many times, no. And that brings up the blue flash. I told you why. The blue sky is fake. You're not going to be able to see blue. I gave this lecture at the Golden State Star Party, and I had 2 people come up to me. One who was a pilot in Southeast Asia, who's seen the blue flash several times, and there's a very well-known amateur astronomer in San Diego came up to me and seen it twice. So people have actually seen the blue flash. Not probably too bad. Okay, here we come to the surprise. Suppose that you observe the green flash sitting down near sea level. You can actually, if you're sitting at sea level and you see the green flash, and you're sitting in a chair, and then you stand up, you can see it again. A second time. How is this discovered? Well, here's a little story. In July 2002, former astronaut Beryat was on board a Russian oceanographic vessel which was conducting research on hydrothermal vents when a green flash was observed by his shipmates on deck 7 and 8 of several decks. What happened? Beryat described what occurred. Some observers were on open deck at deck 7 and others on deck 8. But the decks were only 2.85 meters higher, the deck 8. Five of the people on deck 7 saw the usual red disk of the sun change to solid green just before disappearance. We broke into spontaneous applause. The people on deck 8 were still seeing a red disk. And one of them looked out at us, wondering, what are you talking about? He missed the green flash on his deck, but his two partners saw it several seconds after it had happened at the lower deck. Well, this got them rather curious as scientists, and on July 22nd, they decided to conduct an experiment. Look into this. They stationed observers on decks 5 and 9, and timings were taken in order to quantify the delays relative to the time of the observation of the green flash from deck 5. The results confirmed this delay phenomenon, and Gary and his shipmates made a calculation and compared the predicted delays with the observed delays. I want to get into that. And by the way, the mathematics of all this is worked out in the book in the appendix, so you don't have to go through that. But you want to say, why? How can this happen? Well, it's all laid out. I'm going to go. We're not going to do math here, but I am going to give you a little geometry and take it a certain way, and then we'll drop to an interesting chart, which is what I'm going to get. Okay, here's the Earth. I'm going to get people's. Let's use this. There's the Earth, and here's Alice right there on the surface of the Earth, and this is her horizon. She's going to see a green flash here. And here's Bob. He's up here, E, with a distance E above A. Now, obviously, this isn't the scale because E isn't going to be that length and the radius of the Earth that length. But we have to exaggerate in order to make a point. Bob is going to see the green flash down here because if you draw a line from here to the surface of the Earth, the tangent, you can see the green flash here. And the angle of depression is going to be called theta. That's an important factor to calculate. And by the way, it just so happens that angle happens to be that geometry shows that. Okay, now we want to do a calculation of what that angle is. Well, we can go through the math, but I'll just tell you it's going to be a constant. Oh, well, it turned out to be that. By the way, this is the angle in radian. By the way, does everyone know what a radian is, or how many know? A radian is what scientists use to measure angles instead of degrees. Splitting the circle into 360 parts is artificial. You should make it 300. In scientists, they use a natural angle. If you take a circle of radius r, and you take that radius and you just lay it on the circumference and ask, what is the angle subtended by that radial arc at the center? That's 1 radian. Turns out to be about 57 degrees. And that's what scientists use. So things, if you're doing math and physics, you're going to use radians. But you can easily convert. Okay. Let's see. Okay. Okay. Theta turns out to be that particular angle. Is of no importance to talk about it. And if you have the vertical rate of the sun's descent in radians per second, then the time between the green flash is just that angle theta divided by that vertical rate. And we can calculate both. Now, Gary actually could determine the rate of descent, the vertical descent, because he was there and he had a stopwatch. What did he do? He just measured the time between when the sun first touched the horizon to when it disappears, and so it was about 3 minutes. However, with math, you can sit at home and you can decide exactly what that vertical rate is using mathematics. And that's sort of in the brown material. We're going to skip that. Okay. All right. So it turns out that the delay between the green flashes, that's that theta over r, r is the rate of vertical descent rate of the sun, which he measure because it was right there in that stopwatch. And theta, well, we can calculate that in the appendix in the book. So it turned out that the delay between green flashes is 10.8 times the square root of E. E is the elevation distance between the two people. What's really interesting about this is that's not E, that's the square root of E, and that is what causes the surprise. And I'm going to talk about the surprise now. We're just going to look at a table. And we're going to go through this table and my point will be made. Let's suppose that the elevation is 2 feet above sea level, or 6, or 100, or 104. And let's look at the delay in seconds between the first and second green flashes. From sea level, I'm sorry. We're going to talk about the delay from the first flash at sea level to these other heights. Okay, if you're 2 feet above sea level, 8.4 seconds. If you're 6 feet, 14.6, and then so on for these two. What's really interesting is the difference between that number and that, between the 2 feet and 6 feet above sea level. It's 6.2 seconds, this difference. This difference, however, is much smaller. It's only 1.2. So, what can we make of all this? Here's what we can make of it. Okay, we're at sea level. I'm not going to sit on the ground. I'm going to put a chair here and I'm going to look at the green flash. So I'm going to sit down. Okay, I'm not at sea level. I'm 2 feet above. Okay, 2 feet above. I'm going to see the green flash and I'm going to stand up real quick and look for the second one. How much time do I have to get off my rear from the chair up to 4 feet? Well, you know, I could do that in a second and everybody else can. Well, it's 6.2 seconds between the green flashes. So you can sit in that chair 2 feet above sea level, see it, stand up leisurely, and bingo, see the second one because there's plenty of time. 6.2 seconds. Now I want to make my point here. Suppose that you were not sitting in a chair at sea level, but suppose you were sitting in a chair so that you were 100 feet above sea level, and you stood up. Well, the difference here is 4 feet, just as it was 4 feet here. How much time do you have to stand up when you're at 100 feet to see the second flash? Well, you better do it pretty fast because it's 1.2 seconds. The difference between 1.2. So the point is, if you really want to see 2 green flashes in a row, don't be way up high. Be near sea level, and you can take your time. As I say, we're 59 different topics, and we don't know what the next one is. This is it. There are 2 moons of Saturn in virtually identical orbits. You might think that they would collide, but they don't. What's going on? Well, let's talk about this. You've got Epimetheus is in the lower left, and Janus is in the right, as seen by the Cassini spacecraft in March of 2006, 2 months before swapping orbits. Now, okay, by the way, this picture is misleading. Janus is bigger than Epimetheus. Well, that is, let's see here. Yeah, so it looks bigger, but actually Janus is much further away. The reason is that we're viewing the 2 moons with a small angle between them, so there's foreshortening the distance between them. So this is maybe a misleading image. But here's the interesting thing. You'd think they would collide, at least you might think so, from the following fact. Epimetheus and Janus, about 75 and 112 miles in diameter, they orbit Jupiter in the same direction. Their orbits differ by 31 miles in distance from Saturn. Only 31. Less than the radius of either body. Well, if the distance is less than that radius of either body, and one of them is in the lower, slightly lower orbit, that's going to catch up and slam into the one in front of it. It can't be because they wouldn't exist. So what's going on? Okay, well, let's find out. Okay, those are pretty big letters. I guess you can read that easily. Okay, here we have Janus Here we have Prometheus, and Saturn is down below. So this is closer to Saturn. Saturn's down here. Janus is up above. Well, if you're closer to Saturn, you're going to be moving faster than if you're higher up. So Prometheus is moving faster, and here's Janus, and you can see if they just went in a straight line, they slam right in. So what happens? Well, there's a little dance. As they get closer, they gravitationally attract each other. Well, Janus is going to be pulling on Prometheus, speeding it up. Prometheus is going to be pulling on Janus, slowing it down. Well, if you speed up, you're going to get a little further away from Saturn, and if you slow down, you're going to get a little closer. So what they do is, Janus curves down here, Prometheus moves up here, and so what happens? Well, Janus is now in the lower orbit, so it's moving faster. So it says, turns around and says, goodbye, Prometheus, you're not going to catch me. I'm off, I'm moving faster. So Janus then moves on. So there is no passing. They don't pass each other, they switch orbits, and the one that was ahead speeds up in the lower orbit. Okay. Well, of course, and so Janus will slowly creep ahead of Prometheus now, and 4 years later, they'll do the same little dance. What actually happens is that the total angular momentum of the two moons is constant. The velocity changes cause the inner moon to move a little farther away from Saturn, the outer moon to move a little closer. In effect, the two moons switch orbital places due to an exchange of angular momentum, and neither moon actually orbitally passes the other. And the dance takes about 100 days. They actually keep a rather healthy distance between them, about 9,300 miles during this close-in period. And as I said, about 4 years later, they repeat the whole thing. And the twins' co-orbital situation is the only one known in the solar system. Just imagine if you're sitting on one of these as an astronaut and watching the whole show. It'd be rather interesting. Okay, new topic. Okay. I thought people would be interested in talking about Cepheid variables. Most people know that Cepheid variables, they pulsate, and the period of pulsation can tell you the absolute magnitude of the star. And in red, to repeat that, they pulsate, and their period of pulsation is related to the absolute magnitude. And just think for a moment how important that is, and who the hell discovered that? That's the Nobel Prize. If that's the case, and you see a Cepheid variable, maybe way off in a galaxy or even in our own galaxy, and you measure the pulsation rate, you know its absolute magnitude. Well, obviously you know its apparent magnitude. Get a photometer out, how bright is it as you see it from the Earth? If you know that those two magnitudes, you know its distance. A new way to discover the distance to far off objects. Parallax was really the first method, but that only works if what you're looking at is fairly close. And by the way, this opened up, and Henrietta Leavitt, who worked for Pickering at Harvard, was the one who discovered this. She was given an assignment to look at variable stars in the large and small imaginary clouds, and she, in 1908 and 1912, she discovered this, the periodicity difference. And a mathematician, a Swedish mathematician, Mittag Leffler, nominated her for the Nobel Prize in 1926, and then discovered she had passed away, unfortunately. And you can't give a Nobel Prize out to someone who was dead. But it was a major discovery. And everybody knows about Edwin Hubble discovering the distance to M31, the Great Andromeda Galaxy. Before 1923 and 24, when Hubble discovered this, there was a real controversy. There's this fuzzy object in the constellation of Andromeda. And we've all seen it. You can see it with the naked eye. And ancient people saw it, didn't know what it was. Well, among professional astronomers, there was a controversy about what is that. Is that just another gaseous nebula up there, like so many others? Wouldn't it be nice to know how far away it is? And all of the things you can see in the sky, they're roughly within, we're not the center, but we're not at the fringe of our galaxy. But since the galaxy is 100,000 light years, if you're in the middle, everything would be within 50,000. Okay, we're not in the middle, but everything ought to be 70,000 light years or closer. How close is this thing? Well, the controversy was settled. Hubble discovered Cepheid variables in M31. And he concluded it's 1,000,000 light years. That means this is not in our universe. It's not in our known universe. Everything we see in the sky, the whole Milky Way, has nothing to do with that. That is something a long way away. And by the way, it turns out it's 2.5 light years, not 1,000,000. And the reason for that is there are different types of Cepheid variables, and Hubble was assuming Cepheid variables, he was looking at one certain type, well, they weren't. And so there's a different periodic relationship to absolute magnitude and so on. But it was discovered later and correct. What are those three types of Cepheid variables? Type 1 is a population that consists of population 1 stars. The period is between 5 and 10 days. A classic example is Delta Cephei. Type 2, classic example is W Virginis. Population 2 stars are in that. They're population 2 stars. And the period is at least 10 days. And then there's another type of star named after its canonical example, Lyra. It's lower luminosity star, and the period is between 1.5 hours and 1 day. Well, you can see these are different rates. I mentioned population 1 and 2 star. I should explain. Population 1 stars are stars that are found in the outer disk of the Milky Way. They're brighter, younger, and they have a higher metallicity content than population 2 stars. Metallicity just means they have elements higher than, in the periodic table, higher than, not hydrogen and helium, beyond that. And the word metallicity is misleading. They're not metals and lithium is metals. But they use that word metallicity to say anything other than hydrogen and helium. So population 2 stars, they're older, they're fainter, they have less metallicity, and they're found more in the core of the galaxy and in globular clusters, which of course are generally above and below the core of the galaxy. Okay, I want to explain why Cepheid variables pulsate. It's actually just a little physics, and it's all perfectly clear. Okay, Cepheids, these three types of stars all have a small, dense core. There's a picture coming on the next slide. Small, dense core and a large, low-density envelope enveloping the core. But inside the envelope and surrounding the core is something called a pulsation layer. And here's the picture. The red is the core, PL is for pulsation layer, and then the blue is the low-density envelope. Okay, the pulsation layer is going to expand and contract. The core stays the same size, and it produces energy at a constant rate, no change there. The pulsations arise from variations in the rate at which radiation can escape the star. Well, what's going on here? In order to discuss this, we have to know a little bit of preliminary material, which I'll go over now. Deep inside any star, radiation, which, by the way, starts off as gamma rays, very high energy rays, not visible wavelength light. From fusion, it takes millions of years to reach the surface of the star. I think most people know that, maybe not everyone. Millions of years for a photon at the core to reach the photosphere, the surface of the star? Yeah, okay, we'll explain why. Once photons reach the photosphere, now they're at visible and ultraviolet wavelengths. They stream away at the speed of light in 8 minutes, they get your eyes on the Earth. And if they took millions of years to make it up to the photosphere, free at last, like the genie out of the bottle. Okay, why this is important for our explanation of this pulsation. Why does the light spend millions of years navigating the sun's interior? Photons can, here's the reason, photons can stream unimpeded through gas consisting of neutral atoms. Same number of protons as electrons, they're electrically neutral. Okay, no problem for the photons. But they're scattered by free electrons. If there are a lot of free electrons around and ions, then the photons are going to get scattered this way and that way. The hydrogen and some helium in the core of the star is ionized. So there are a lot of free electrons and ions. And it's very, very dense. For a hydrogen atom, the electron in the hydrogen atom, if it's ionized, is not bound to the proton. So hydrogen atom, you got the proton, and this electron says, bye-bye, I'm free. For a helium atom, the other type of gas we're talking about, well, there are two protons, and there might be two or more neutrons depending on the isotope. Neutrons don't matter, they're not electrical, they have no electric charge, but there are two electrons. So the helium atom could lose one of its electrons, singly ionized, or two. That creates more free electrons. Okay. Okay, the plasma and the ions and plasma, which is basically the free electrons and the ions, it's very, very dense in the core, so that the photons are constantly being scattered in random directions, mainly by the vast number of electrons. The photons can barely make headway toward the surface of the star. In mathematics, this is called a random walk. In statistical mechanics, this is very important. Einstein used it in his Brownian paper on Brownian motion. Let me explain what this is basically a random walk. The photon it's a random walk. So what are we talking about? Suppose there's a light, that classic example of the random walk. There's this drunk man, and there's a light pole, and he's hanging on it, and he desperately wants to, get about a mile away. And so in his stupor, he steps away from the lamppost and walks this way, and then he walks that way. And every time he takes a step, it's in a random direction. And you can ask, well, okay, you can ask, what's the mean time required for him to get to where he wants to go, a mile away? Well, this is what we have here. Only the analogy is the light post is the core of the sun. The man is the photon, and the mile away, the distance the man wants to get, is the photosphere of the sun. And what's the randomness? Well, randomness is not due to optical here, it's due to free electrons and ions. So we're almost there. Now we can talk about what's going on with the secret variables. Okay. This is the beginning. Excuse me, the beginning of the pulsation cycle. The pulsation layer contains singly ionized helium. This allows radiation to pass from the core through the pulsation layer. There are not enough free electrons to slow the photons down much. So, okay, we've got some free electrons here, but not enough to stop us getting through the pulsation layer to that envelope beyond. But some of the radiation increases the temperature of the pulsation layer. Singly ionized helium atoms become doubly ionized with increased heat. Many more electrons. Radiation is now almost blocked from passing through the pulsation. The pressure from the blocked radiation causes the pulsation layer, that yellow annulus, to expand outwards, and that blue envelope, the outer envelope, under pressure expands. The star is expanding. Okay. But as the expansion occurs, the density starts dropping, the temperature of the pulsation layer drops, and doubly ionized helium atoms recapture an electron. So now they're singly ionized. Gravity and the reduced outward pressure cause the pulsation layer to subsequently contract to its former state, causing the star to contract. And then the process begins all over again. And Arthur Eddington was the first to characterize this activity in his 1926 book, the internal constitution of the stars. So now you know basically why you have this pulsation occurring. Now I'm going to, I have one more topic that's totally different. Why the night sky has dramatically changed over the time of human civilization. Do we have time to go through all of this, Jason?
Yeah, save time for questions also, but yeah, go ahead.
Yeah, can I do
Yeah,
this,
yeah,
or should we
yes.
skip this? Or?
Go ahead.
Oh. Anybody wants to leave? Okay, this is completely different. We're going to talk about something much more general. It wasn't until about the 12th century CE period that Polaris might reasonably call the pole star. During the Roman Empire, there was no pole star. And the ancient Greeks, about 350 BCE, they could see the Southern Cross from the Mediterranean. You can't see that now. And this is a very interesting diagram. Here's the Little Dipper, and there's Polaris. And in the next slide, you'll see the Earth is spinning, its axis is spinning like a top. And so it spins once every 26,000 years. So that the axis is pointing to the celestial sphere, and so it's circling around up above in the celestial sphere. The north celestial pole is tracing out the circle. And, well, here it is. Here we are. There's Polaris right there. There's a little different. And if you go back to the time of the pyramids, that star, Thuban, and this is Draco, that was the pole star. And in the future, this is where we're going to go. If you come around here, Vega, very bright star. Well, it's going to be 5 degrees away. That's fairly long distance. Okay. Yeah, it's interesting that Thuban got only within 10 arc minutes of the North Celestial Pole. And Polaris is now about 40 arc minutes. It's going to come within 27, but not as close as Thuban. But then Polaris is second magnitude. Okay. At the time of the ancient Greeks, the summer solstice was in Cancer. Did we skip that? No, we did skip it. Yeah. Here's the Earth. Here's the Earth's axis, and it's spinning around, as I say, like a top. And right here, here's Polaris. This is the Earth's axis. This takes 26,000 years, about 13,000 years. Vega will be here. There's Thuban. A couple thousand years ago, it was the North Star. The cause of this wobble, what's the cause of it? It's the combined gravitational attraction of the sun and the moon on the Earth's equatorial bulge. That's what's causing. If Earth didn't have an equatorial bulge, this would we have. And why do we have an equatorial bulge? Why is the diameter through the equator wider than through from pole to pole? Well, the Earth is spinning, and so it's a bulge out. Centrifugal force bulges the Earth out, so we have a bulge. So here we have, this is the ecliptic. That's the path that the sun would take in the night sky over 1 year. The ellipse creates, you can talk about the ecliptic plane which passes through there. And this is the equatorial plane. It's, of course, the plane perpendicular to the axis of the Earth. And there are 2 points where these ellipses intersect, the vernal equinox and the osmium equinox. Now, since this equatorial plane is wobbling around, those 2 nodes are going to move along the ecliptic precession of the equinoxes. That's what it's called. Okay. At the time of the Greeks, the vernal equinox was in Aries. And currently it's in Pisces until 2597. And then it moves into Aquarius, the dawning of the age of Aquarius in the 60s. I'll just skip some of the other stuff that occurring here. Okay. At the time of the Greeks, the summer solstice was in Cancer, the winter solstice in Capricorn, and we call these circles of latitude Tropic of Cancer, Tropic of Capricorn, and that's where the sun, if you were there, that's the highest any point higher than the Tropic of Cancer, you'll never see the sun directly overhead. If you're on the Tropic of Cancer or Capricorn, you can see it when the sun gets highest in the sky or lowest in the air. And in between, twice a year, you'll see the sun overhead. Well, because of the precession of the equinoxes, these solstices are now in Gemini and Aquarius. And the conclusion is that the North Celestial Pole, that's the spot that the North, that our axis is pointing to, is shifted position in the night sky, and so all points on the celestial sphere have changed position. I might add that since the solstices are now in Gemini and Aquarius, not in Cancer and Capricorn, not in Cancer and Capricorn, should we change the name of the Tropic of Cancer and Capricorn to the Tropic of Gemini and Aquarius? Well, nobody does that. The old names have stuck, even though they don't correspond with the constellations now. There's one other argument, there's one other argument to show you how the night sky has changed because of this wobbling. Here you have the Earth. Here's a latitude, a circle of latitude, and you're sitting right there, and that's your horizon. The axis is tilted this way, and you can see that star is well above your horizon. I can see it. What happens 13,000 years later at the other extreme? The axis is now pointing in the other direction. There you are. There's your horizon. Oh, can't see the star. So things change over time. Let's see. Yeah, I'll try and go quickly through this. There's a second factor affecting things, and that is that the ecliptic plane that the ecliptic forms, that's the path that the sun takes, it actually changes slightly. And so the angle of obliquity, the angle between that plane and the celestial and the equatorial plane, they shift slightly, but not too much. And I'm going to skip some of this. The angle between the two can only vary about plus or minus 3 degrees. Right now, the angle is about 23 and a half degrees. The average is about 23.3. So that doesn't really make much of a difference. But there's an interesting little story here. It doesn't make much of a difference in the sky, but on land it does. Currently, the Tropic of Cancer is close to the average position, but it's changing at about the fastest rate, and it's about 45.5 feet a year. In 10 years, that's 1.5 football fields. And in 1908, the Japanese colonial government in Taiwan erected a concrete landmark at the spot where the Tropic of Cancer crossed a newly completed railroad line. Since then, the Taiwanese government has made that area a park, but now the Tropic of Cancer has moved entirely out of the park, and the administration cannot acquire more land. So there's some effect. Now, I'll just say one thing about why does only plus or minus 1.3 degrees that angle of obliquity change? It's because of our big, beautiful moon stabilizing things. What about Mars? It's just got a couple small moons. They don't affect things much. Mars can have an obliquity change of 40 degrees. Oh, yeah, that's a lot. So if you're one spot on Mars, a long time later, it could be a very different climate at that spot because of that change. Okay. Okay. Getting what's a year?
Oh yeah, yeah.
You might say it's
We should
Yeah. You,
okay.
Yeah.
Let's
you're,
okay, let's do that. Okay. Questions? You can't stop me, Jim.
I'll insert my president
I'm
thought
getting
party.
intended to talk too fast. And I said, I'm not going to do that. It's not a good idea.
Oh, yeah.
That's,
There are
Don't get through it.
59
Oh,
topics
get the
in the
book
book.
and
Yeah.
And Michael, by the way, let me just mention, I do have 4 books here that Arthur copy sent, and I can sell them for less for cost. But you can go online and, of course, get them at the top. So, any questions?
So questions, yes.
Does the behavior of Pluto and its
I'm going
moon,
to step down. I have hearing aids on.
does the behavior of Pluto and its moon, is that seen anywhere else?
Say that again.
The behavior of Pluto and its moon?
You said Pluto and
And its moon.
And its moon?
Charon, the moon.
Yeah,
What about them?
the double thing?
Yeah.
Is that happening anywhere else in the solar system with other?
No,
planets?
there's no other. Well, Pluto's no longer called a planet, but among the planets or dwarf planets, no, there's nothing like that. Yeah, Charon is half the size of Pluto and 12,000 miles between their centers, and so no, that's not the case. The very center of no 2 objects has, reasonable size objects have that property.
Another question?
Why does Pluto exist? Why is it out there?
Why does Pluto exist? Well, you could ask that about why does the Earth, the Jupiter, etc. Why do any of these exist? Basically, our sun condensed out of a gaseous cloud, collapsed, the sun formed, and then you had the disk of the sun. You started getting material agglomerating together, creating planets, and Pluto was one of them. Well, so it's the same for the same reason that all the other planets exist. Pluto exists. Some of them have moved around in position since they were formed, but that's another story.
Yeah, one more.
For Miranda, would you share about that? All the.
I'm going to start.
Here, I can go.
Okay.
So, for the planet, the moon Miranda, you showed all these different terrains. Is that all the same material, or is it different types of like?
Well, the short answer is I don't really know. I mean, this is one thought why it's such a freak is at one time they thought its orbit around Uranus might be elliptical, and so there would be tidal gravitational stretching, causing liquefaction, and so then when it became more circular, there's upwelling material in the frozen place. Io, the moon of Jupiter, that famous moon with all the volcanoes, this gravitational tidal action is stretching. Io is the closest of the 5 Galilean moons to Jupiter, and the gravity is so intense there that there's stretching. It's because it's not a perfectly elliptical circular orbit, so it moves closer and further away, and so you stretching. It's like dough. You keep stretching, it might heat up. Well, it's heating up so much in Io that you got volcanoes, and in the case of Miranda, it'd be a much milder effect. But they don't know. They don't know, and we haven't even seen the other side, which is.
We don't have any idea of the geology of the planet.
Pardon?
We don't know anything about the geology of the planet, right?
Well, they don't know the geology. There's a sample of material on the surface that just flew by and took images and certain measurements, but nobody's sampled the material there. We all
Well, last one. Last question.
I understood the phenomena of the pulsing of the stars, but what about that phenomenon allows us to determine the magnitude and the distance?
Okay. By the way, on these topics, there's much more on each of these topics in the book. I'm going to say that because I have charts showing the relationship. And basically, the longer the pulsation rate, the brighter the star. But that can be quantified. They have a chart. If it's a type 1 Cepheid, here's the absolute magnitude, and here's the pulsation period. And so you can see, there's the curve, and here's the pulsation rate is here, you go up here and over here, that's the absolute magnitude. But there are different tables for the 3 different types of Cepheids. And Hubble happened to be using the wrong one. Type 1 Cepheid, it's a little different. The tables are a little different, but they all have that critical property of pulsation rate related to absolute magnitude. But I go into some of these topics, I picked material on gave a lecture that was in fact too long.
Well, Dr. Douglas, thank you.
Thank you very much.
And if anyone has more questions, I'm sure he'd be happy to talk with you further. So, thank you.
Thanks, Jason.
Hi.
See you guys. Thank you.
Oh, thank you.